All right, so let's get started. So thanks everyone for coming out to exit presentation for Chuck and Aaron, and Samantha is also doing her presentation practice for her exit, which is at the end of next month.
Sweet. Thanks, Jim. So next, this is kind of a picture showing what our application ideas for the project H.O.M.E are. So the idea is that soft robotics or soft robots are really adaptable robots. So we can have these modular robotic systems, and then we can have them be used for a lot of different tasks. So we could deploy these on a lunar, Martian, just a different surface, a different planet, and we'd be able to do a lot of different things. So you could use them for things like just surveying and exploring. So you could have them roll out and do survey different areas. You can also have them as like these large bladders on the sides of habitats. You could store like water in them. So the cool thing is that the soft robots can either be inflated with pneumatics or hydraulics, so air or water. And water is actually a really good radiation shield. So you could just have these bladders of these large soft robotic panels, and they could be an extra form of shielding for temporary or more long-term habitats. And then we could use them for kind of channels in between different habitats. You could also use it as like dust protection shielding. So there are just basically a ton of applications where you could use these soft robots because of how kind of modular they are and how adaptable and squishy they are. And one of the main ones that we actually are working towards is the idea of being able to build these temporary structures you could then lay regolith on, which is like lunar dust. And you could use that to make a longer term structure. So you could use your set of, 20, 30, whatever robots and build multiple temporary structures to build long-term structures with material in situ resources that are on the moon, and then that could rigidize, and then you could have your robots kind of disassemble, move away, and then build something else later. This also, H.O.M.E fits into the larger in-space assembly work that's going on at NASA Langley. So we've been doing in-space assembly research since the decades ago, so the early 80s, 90s. Actually, this picture in the top here is a telescope assembly demo that was fully autonomous that was done in the 90s, led in by Bill Doggett's group. And so we have this concept of if you want to have bigger and better things in space, you have to be able to assemble them there, because right now you're restricted by launch vehicle size, so you can only get so much material up in one launch. So if you want to get, for example, James Webb Space Telescope to get that huge 6.5 meter telescope and a 5 meter fairing, it had to be folded really complexly, and there's a lot of deployments that have to go perfectly when it gets into space for it to be a successful mission. And that puts a lot of more design restraints on your actual whatever that scientific instrument is. But in-space assembly can allow you to have multiple launch vehicles that go up, and then you have multiple parts, and then you can do all the assembly in space, and you get your final assembly where you want it, and it can kind of reduce launch loads for all your different components. So we've been doing research here with different robotic manipulators. So we have these long-reach manipulators like LSMS, the Lightweight Surface Manipulation System, and a talisman arm. And so we've done a lot of demonstrations with these. We've even done really high-precision truss demonstrations. You can see, actually over to the right, we have a truss assembly demo where we used a team of heterogeneous robots, where we have a long-reach manipulator and then an end effector robot that can hand off these truss struts to another robot that's on a turntable, and that robot, called Ninjar, can actually precisely position the truss joint. So the idea is that you use these multi-robot agent teams to build whatever structures you need. So H.O.M.E is just one example of how you could use soft robots to assemble things in either space or on planets. And then another project that's close to H.O.M.E is called Assemblers. So Jim is also in charge of this project. And it's another idea of using these multi-agent systems, but in this case we have these stacked Stewart platform robots. A Stewart platform's just a robot with a base and a top, and then they're connected by 6 linear actuators, which gives them 6 degrees of freedom and high precision control. So it's another idea of it's a hard system, but it still carries the idea of having modular robots that can reconfigure to complete an assembly task. And actually, later in the summer, I'll be working on making a soft version of a Stewart platform to try to do something like this. So it'll get all connected, which is cool.
Right. So now let's go into the work that H.O.M.E did. When I got here at the end of the furlough, Jim said, we're going to use soft robots to build things on the moon. And I was kind of like, what are soft robots? Which is a question we all had. So this right here is on the right is sort of a graveyard of a lot of soft robot morphologies we've gone through. So our initial investigation for the IRAD project was to familiarize ourselves with soft robots and actually make some of these things and understand the manufacturing processes and the sort of advantages and disadvantages of them. And then also kind of look at the lay of the land and understand the state of research going on, which is not all that much. It's a pretty new technology. There's a couple labs looking into soft robots, but as we'll probably mention throughout our presentation, there's just a lot of new things going on and not a whole lot of supporting work. So once we familiarized ourselves with soft robots, we had to decide what we wanted to do for our project. And so that meant sort of developing the mission ConOps that we talked about earlier, kinds of things that soft robotics would be advantageous for in terms of in-space assembly and exploration. And also, so once we determined kind of where these soft robots would fit in, we had to find what capabilities we needed these soft robots to have to be able to accomplish the tasks that we set out for them. And so that sort of snowballed into planning and figuring out where we wanted to take the IRAD project. If you go to the next slide. So in all of those discussions, we kind of came up with 4 things that we wanted our robots to do. So the idea was you have a multi-agent system where different robots meet up together, build structures, break down, move, meet, build, repeat. So in order to do that, one, we needed them to move. We needed them to be able to traverse across a surface. So we investigated quite a few methods of mobility. One is this sort of gate walking design, and you can kind of see on the table there's a hexapod. So there's a lot of ways to get these things to move. We settled on one for our final design here that we'll show you. But yeah, the next is joining. So we needed these robots to be able to join and interact in a significant way, to not be able to break apart. Next is rigidization, and shaping. So once these robots are in place and joined together, we want them to create the shape we want. So if we're talking about pouring regolith, let's say we're making a solar array for a solar farm. We want them to pour regolith at certain locations and give a certain angle so that we can place mirrors on top of them to point directly at an energy collection device. So we want them to be able to create the surface we want and then harden in that shape. So down here in rigidization shaping, we investigated some laminar jamming techniques, which are multiple pieces of paper stuck in a vacuum. That was mildly successful, but also there's no, like when you're in a vacuum and you pull a vacuum, it doesn't quite work the same way. And then we also came up with this idea where we have a low temperature thermoplastic embedded in the silicone, and we'll talk a little bit about that going forward. So yeah, these are the 4 capabilities that we came up with that we sort of developed through the spring. So the spring was spent making unit tests and proving that these things were all possible within the realm of soft robots. Okay, and so one of the big things we came up with was this rigidization technique of a low melting temperature thermoplastic embedded in silicone, which silicone is the main material we've used for our robotic manufacturing. It's easy to work with, it's quick to prototype, you can fix it really easily. We embedded a heater wire inside of this blue plastic, and then we embedded all of that into silicone. And you can see it here on the bottom. One of the advantages of this, and one of the advantages of soft robots, is that everything is very compliant and can deal with damage very well. So one of the cool things about this is it's a rigid technology that also heals itself. So the plastic will melt when you heat it up and soften, and you can do the things you need to do to move around. And then when you cool it down, it will harden in place. Now, if it's hard and you hit it too hard, it will break. So you can see here, we've intentionally broken this piece of plastic here. And then once you helt it, it will melt and reflow back into a solid material. So here in the bottom, we have the brakes are put in, and the plastic won't hold up the weight. In fact, I had to hold it there just to get the picture with solid material. So here in the bottom, we have the brakes are put in, and the plastic won't hold up the weight. In fact, I had to hold it there just to get the picture. And then we melted it and heated it up and then let it cool, and it can hold the weight all on its own. Now that we have these things, now that we're able to move, join, and all this, we need to be able to control these things and get them to do all those things together. So we started with this control board here on the left, which is from the Soft Robotics Toolkit. It's a toolkit put out by Harvard, and it's a kit you build yourself. It has 4 pneumatic outputs. So one of the primary ways of driving these soft robots is you have these pneumatic channels inside of them, or pneumatic networks, and you inflate them, and that's how they are able to move around. So we had 4 pneumatic outputs, but we decided that wasn't enough. So eventually we expanded that into a total of 16 pneumatic outputs, and you can kind of see the mess on the bottom. That is our current control setup, and we'll show it off back there. We are able to accurately control 16 pneumatic outputs. So the one on the left is the second version, but the one on the right is the first version, and it's fully featured with PID control, feedback for sensors, and we can do state-based choreographic control. So we can monitor the robot's state and then tell if it's in the right position and then move on to the next state, and that allows us to get like a walking gait moving forward. So now that we can build these robots, we can get them to move around, we need to be able to evaluate their performance and how well they do the task that we want them to do. So that sort of started off in the spring as this evaluation platform where we had a soft robotic finger, and we were kind of seeing how much force that finger was able to get based on the amount of inflation and kind of some basic properties of the soft robots. And then that eventually evolved into, well, we're going to have multiple soft robots on the table, and we're going to need to be able to monitor all of them. So we've actually set up a Vicon system in a lab in 1238 that will be able to monitor all these.
So Chuck just gave you an overview of what was done in the spring, and then coming into the summer, we wanted an awesome demo to show all of these different facets of soft robotics that we could bring together. So this were our summer test objectives. So the idea is that we start with 2 different robots, and they're separated, and they're both basically copies of each other. So again, it's the idea, it's a modular system where you have repeated robotic units. So you can easily swap them out, and you can manufacture them the same way. And then the robots will actually use a chainmail design that's embedded in the robot, and it's going to roll the robot up. And then when the robots are rolled up, then they're going to actually use the new nets, so these pneumatic chambers on the outside of the robot, and those are going to inflate and cause the robot to roll. And then once it rolls to a new position, it's going to unfold. And for this setup, we have so many new nets. We're going to have one robot do all the rolling, and one robot's going to already be sitting kind of down, getting ready for its robot friend to come to it. And then it's going to unfold, and then we're going to have a joining mechanism so that the robots will be stuck together. And then now we have a new robot unit, because now it's no longer 2 robots. It's 2 robots that are connected together, and they have that joint. And so now they can both roll up, and they can create a new structure. And then each robot also has the PCL or thermoplastic that Chuck had mentioned. So during all of these movements, those are going to be very warm and compliable so that we can do all of the rolling we want, unfolding, etc. But once we reach our final desired shape, we can actually turn those off and cool them down, and then it'll rigidize and keep that final shape that we create. And then just like a bigger vision, again, like in our idea going through the summer, we were thinking, the grand dream is to have these modular robots used where you have so many of them that you can make really big structures. So right now we're going to show you with 2 modules over there, and it's going to make a structure that's about 1 meter long, which is really impressive for soft robots. A lot of them are really, really small. But you could take these half-meter robots, and you could just have so many more of them and do the same simple joining and create larger and larger structures. So that's kind of a very future goal.
All right, so to accomplish our test objectives and to show those 4 qualities that we determined were important in the spring, we decided to combine multiple systems for both actuation and rigidization. We're using, for example, if you look to the top left corner, we're using the pneumatic nets as a way to inflate, But to get the robot into a position where inflating can actually cause locomotion, we're integrating a chainmail system, which we discovered chainmail is very compliant at first, but as you continue to bend it, it will jam and become rigid. And so it allows you to be soft and hard at the same time. With that, we can combine that with the PCL that Chuck mentioned earlier, and we can use the motors on the chainmail to hold the robot in place as the PCL hardens to help it maintain its shape. And then once it maintains its shape, we can let the motors go if we desire. Another thing is we're actually integrating the PCL into the pneumatic nuts together for a joining technique. Unfortunately, that won't be demoed today. We're just going to use a plain pneumatic joiner, but in the future, that's a design that we will continue to improve. These are our two robots, and we decided to name them Sonic and Tails because of the colors. So Tails is the yellow one, Sonic is the white or the gray and the blue one. And as I mentioned earlier, they have all the systems embedded into one. It's a combined, integrated soft robotic system that we will be demoing for you after this presentation. For mobility, we decided to combine the pneumatic lines and the silicone of the robot and use the chainmail to roll it into place, and then inflating and deflating those pneumatic lines at a certain pattern will cause the robot to roll, giving us a gross locomotion. What we discovered is that these robots can really take a beating, and we can inflate those pneumatic nets out pretty far from the base of the robot. And if you hold on for just a second, you're going to actually see the robot complete an entire roll on. There we go.
It's a big deal.
Yeah.
It's a really big deal.
Yeah.
Yeah.
And then if you hold on for just another second, we're going to have
That's a long second.
there we go.
There we go. We're very excited.
Yes,
Big deal.
yes, it's the farthest we've ever
Yeah.
gotten a soft robot to move. Now for rigidity, like we mentioned earlier, we're going to use both the chainmail and the PCL. As you can see, we're using the chainmail to shape the robot into the form that we want. And then once it's held into place, or once it gets to the form that we want, we can hold it in place, let the plastic cool, and then it will stay in that form or somewhat of a version of that form. As I mentioned earlier with the chainmail, that's just cable driven. It's really easy to control. You know what you're getting, and it's just a fast way to help get things into shape. And then going into a little bit more detail about the PCL that we're using, it melts at about 60 degrees Celsius, so doesn't take that much heat. What we did is we 3D printed a custom shape of this thermoplastic and then embedded a wire while it was 3D printing, so that way we could have a form to heat it. The robot will soften, or the plastic will soften, and that will allow the robot to be flexible and compliant when we heat it, and then we let it cool off, and the robot will harden to the shape that we desire. Another interesting property, as Chuck mentioned, is that the PCL is self-healing, so if we break it, we can just reheat it again and let it flow over, and it will reform itself.
Cool. Yeah, and then the last thing, the joining system. Right now, you're going to see this joining system, which is kind of interlaced fingers that are very tight together, and then when they inflate against each other and cause a bond. But I've been working on doing a different joining system that would actually allow the robots to be modular, because right now you have to kind of lace those together yourself. I think after this video finishes, this is another version I've been working on. It didn't quite get finished for this demo, but having a kind of a male and female system that can be folded down and have enough wiggle room that you don't have to be perfectly aligned, and then when it inflates, it should be able to kind of lock it in place. So that's still in the works. So the nice thing about soft robots is we actually had my newer version of the joiners on the robot. We found out it wasn't going to be ready for today, and we could cut them off and put our old version on, and it's going to work today. Well, we show you. So it's kind of a really cool prototyping atmosphere that's not super, I'm not used to it in hard robotics. It's a lot more forgiving, which is cool.
Soft robots are hard, ironically. It's all very difficult. There's a lot of things that just aren't being done. One of those things is talked about here. Yeah, so Modeling a soft robot is not really done. We toured a soft robotics lab at Oregon State University over the summer, and they asked us if we were modeling all of our stuff, and we said no, and they go, oh, we were kind of hoping you'd tell us how to do it. But as Sam mentioned, they are quite forgiving, so we are able to repair them really quickly. We're able to go from one idea to another in the time span that it takes to 3D print whatever idea we have and then mold the silicone in it. And so we built these robots in about a week after coming up with a final design in ConOps. So part of this internship was great because we developed new technologies. So there wasn't really any work done in joining, rigidization, shaping, leveling. All the things we did are kind of new in the space of soft robotics, and we're pretty excited about that. As well as hybrid soft and hard robotics. Usually you see, like, if it's a soft robot or a soft robotic paper, it's a soft system only. So moving forward, we want to take a look into a lot of different aspects. So like I said, modeling is very difficult. So that makes control very difficult because silicone has up to 900% elongation without going into some plastic deformation or tearing. So we can inflate these a lot, and that makes it really difficult to understand what they're going to do and when they're going to do it. That combined with a sort of kind of at-home hobbyist level of manufacturing techniques that exist nowadays, it's hard to repeatedly make them the way you want to. And so each soft robotic manipulator, even if they look the same, all act completely differently. So instead of spending a bunch of time learning how to model these, we have sort of decided to go the reinforcement learning route, where we set up a system where we have our control board that has a bunch of sensors on it that collect the state of the robot and then sends that back to a computer. The computer will collect that state, kind of select a next state, and then send all that information back to the control board. And the control board is able to do the micromanagement of the control algorithms and get each actuator into the state that it wants to be in. And so essentially it's this cycle of the robot will try to move somewhere and then read what it did and determine if it was a good decision and then kind of run a reinforcement learning algorithm to teach itself how to walk rather than us learning how to walk from principles. And so all of this comes into a sort of multi-agent framework. That's a huge topic in in-space assembly. Like Sam mentioned, there's a lot of heterogeneous robotic systems that are doing complex tasks using different robots. And so part of the work being done for this and assemblers, and Jim can probably expand on it a little bit if he wants, is these multi-agent systems. So we have flocking over here in the corner, of how multiple agents will operate in a space and avoid each other and know where they are relative to each other. So yeah, I'm not hugely well versed on this subject.
Okay, this is work for the fall.
Yeah, so this is all work for the fall, which we did get. So it was a 1-year IRAD, and we did get a second year of funding after doing our midterm review and all the work that they saw us do. So that's exciting.
Thank you.
Yeah.
Yeah, so
Short answer, yeah.
Yeah, great question. Short answer, yes. And additionally, a lot of the materials we're using are very much for prototyping reasons. So kind of this is very much research and development of how you could do these techniques, and then that's a whole different step of how you make it space ready that we're not broaching yet. It's an engineering problem, exactly.
This is more of a feasibility study to
feasibility.
see if soft robots fit within the space of in-space assembly.
Yeah. Because you could even use materials like not silicone. You could use like Vectran or Kevlar, which they use for like large inflatables on the International Space Station. So those are definitely space rated. And you could do similar things. But great question. So first thing we're going to do is we're going to roll up our first robot. So we're going to use it. We're going to control it with Aaron's phone. We have a Bluetooth controller or Feather on board, and that controls 2 motors, which are hooked to the either other end of the chainmail, and that's going to cause it to fold. And so the only reason we can do this right now with the PCL embedded is because we already heated up the PCL while we were presenting, so it's nice and warm,